Welcome back. We're going to be going through the introduction to momentum here. So I'm assuming that you have understood energy and the basic concepts of energy and tried problems on that successfully. And from there, we're going to go and figure out what this idea of momentum is, and also then how does it relate to energy and everything else that we've done thus far. So let's get into it. First, we're going to start with something that you've probably seen before, and maybe you don't know what it's called. We're going to start with something called a Newton's cradle. So if you search on YouTube for Newton's cradle, this is the video that I just had up. It comes up almost right away. Let's go ahead and do it together. Newton's cradle here. And I'm going to go down to the physics of Newton's cradle. I didn't watch all of these. I'm sure there's other good ones. But I'm just going to use this as a demonstration here of what this device is. So let me just rewind it to the beginning. You've probably seen something like this before, where all it is that you have two metal rails on the front and on the back there that are just providing structure for this thing, and at a base here so it's nice and firm. And then you just have like fishing wire that's tied from one end and then goes down to one of these sphere balls, and they're nothing special. It's just solid steel, and so they're very hard and firm. And you need to know a little bit of something about solid steel. If you think about a golf ball for a second, let's take a golf ball, because that's a really hard object as well. If you take a golf ball and you drop a golf ball on a concrete surface, does the ball bounce well? And if you've never done that before, go grab a golf ball from someone in your neighborhood, or don't, because COVID. You go find a golf ball and drop it on a hard surface, and you'll find that it bounces really, really well. So the point here is that some objects that bounce well feel squishy and rubbery, and you might say are elastic. And other objects are so elastic, you might say, or so good at rebounding that it's really hard for you to squish them, and in your hand it doesn't feel like they're squishable, but they really are. And so a golf ball is a good example of that. It doesn't feel squishy in your hands, yet it is a very elastic object. It's like a super bouncy ball, except even better. And you can go ahead and compare it next to a super bouncy ball if you have one, and you might be surprised. Well, a solid steel ball, this is actually a ball bearing here, like you'd have ball bearings in any like axle or something like that, anything that has to like rotate, any bearing. They're just solid steel, and if you take solid steel and you let that bounce in a similar way to the golf ball against the concrete, solid steel against like a solid steel plate, that bounces even better. So the point here is that these things bounce really well. So now I just have he has 5 of these steel spheres in a row here, and they're just suspended. Notice that there's a little hole at the top. So the fishing wire, and there literally is fishing wire here, comes down here. It's like tied and glued up at the top there. It comes down here and just feeds right through there, so they could slide like forward and aft into and out of the picture right now, and then up, and it's tied on the other side over there. And they're supposed to be all at the same height, and most of the ones that you go and you buy none of them are made that well. It's actually really hard to find one of these made really well, and it's been one of my projects to actually make one of these myself so I could actually make a better one. Let me get this a little bit bigger. But you'll notice that he's got some inconsistencies in his, as most of them do. If you look at the bottom here, you can see it, or you can actually see it at the top there, that they're all not at the same height. They're meant to be, but tying these things off, they were rushing through the job here, and you'll see that one's a little bit higher than another. And if we change the camera angle so we're at his hand and we're looking like down the length of this thing, you'd see that they're like all not perfectly in a line. So they should be. So ideally they should be. He's going to, you could imagine, or we don't even have to watch you could watch the whole video if you want. I haven't actually watched the whole video, so I don't know entirely what he says, so don't necessarily take what he says as being accurate. I don't know. The point, though, is that if you took one of these spheres and you pulled it off to the side, if you let just one of the spheres down, it's going to come down and it's going to crash into the other 4 stationary ones. Well, what will happen after that? And you can make some prediction. And if we go and we watch him do it, and if we were in class, I would, go and show you doing that specifically. And I think he does it in this case here. He lets one go down in, and basically one comes out on the other end. And I think I have it on double speed here. No, I do have it on normal speed. Let me do it on slow-mo there so you can actually see it a little bit better. Only one comes out on the other side. Now, in actuality, some of the others move in the in-between. I'll talk about that in just a second here. Don't worry about that for right now. But if he lets one go, which he will in just a second here, as he brings it up, what type of energy does he give it? Gravitational potential energy, I agree. So he gives it a bunch of gravitational potential energy, and then when he lets it go, that thing falls down. And as it falls down, what happens to the energy? Gravitational potential energy decreases and kinetic energy increases. So that basically right before it hits these other spheres there, it has the least amount of gravitational potential energy and it'll have the most amount of kinetic energy. Okay, cool. Then what will happen? Well, now notice that as it went down and hit these things, basically the one on the end moves off and basically the other ones haven't moved. Now in actuality, they do move a little bit, and that's part of it is due to the inconsistencies of the height and alignments, as we were talking about. The other part is due to just the sphere balls not being perfect bouncers. There's a little bit of something else going on in there. But overall, basically one came in, hit all of these four, but then really only one came out. Okay, that's interesting. Let's get back to the notes here. And maybe I'll sketch, for my notes, maybe I'll sketch these things. So we had 5 spheres here, 1, 2, 3, 4, and then I took this 5th one and I brought it out here, and they're suspended by strings. And this one's suspended by a string now. And if I take this guy and I let it crash into there, the outcome of that we saw was 1, 2, 3, and then 4, because this, we could even label it. Let's go ahead and let's label them left to right. 1, 2, 3, 4, 5. So we can be consistent. So this is the 5th one, 4, 3, 2, and then afterwards this first one then came out. And so it looks something like this. That's not so bad. And then this one kind of came out that way. We'll kind of show some motion that way. So, that's probably not too surprising. You probably guessed something similar to that. Now, let's think about it. Let's do a slightly different experiment here. What if, instead of just taking one out, what else could I do? What if instead we took 2 of these things out? Whoa, getting crazy here. So we're going to take 2 of these things out, and we'll number these 1, 2, 3, 4, 5, and it being consistent between them. Now, if I let these things go, what's going to happen? So obviously these guys are going to come down and crash into that. And what's going to be the result? What will happen after it crashes into it? I don't know. Will 1 come out? Will 2 come out? Will 3 or 4 or 5? That's kind of an interesting question here. Let's think about it from our gravity perspective here. Yeah, at the beginning here, we said that UG was at the max, you might say. Well, maybe I'll put UG max up here. And then as it came down in here, kinetic energy was at its max instead, and UG was at its min. Okay, well, you can do LOL diagrams. I'm just kind of doing it. We can even say K is equal to 0 up there. All right, so then, the same thing is going to be true over here. We're going to have the gravitational potential energy be at the max there and kinetic energy be at the minimum, since I'm just dropping it in there. And then right at this point here, we'll have UG at the min and K at its max there. Okay, great. So then what's got to be true about energy? We know energy can't be created or destroyed. So then after this interaction here, after this action, as we did in the last unit, of them colliding, then something's got to happen, and this energy's got to stay the same. Well, we know that kinetic energy is just 1/2 mv squared, and what's the mass in this case? Well, the mass is the mass of 2 of these things in this case, and over here in the previous example, the mass is just 1 of those things. Okay, great. So, we might say mass of 4, 5, because it's the mass of both of them. So then, as this thing comes out, however many come out here, we know that over here, How do I want to draw this without knowing how many come out? We'll draw. Maybe I'll draw some of them in the middle. Let's assume that there's going to be at least a couple of them down here in the middle, and maybe one or comes out, maybe two come out, maybe three come out. Who knows? But we know that something's probably going to come out here, so there'll be at least one. Oh, that's a little bit bigger. There'll be at least one coming out here. Who knows how many? Well, we're going to try and figure that out. But how many might come out is kind of the question here. Well, we know that the kinetic energy, like right as they're coming out here when it's at its max there, has got to be equal to the kinetic energy that was beforehand. This kinetic energy, we'll say, just before the collision is the original kinetic energy. And then the kinetic energy after the collision here, after that action there, will be just the kinetic energy final, or the total, the kinetic energy after something, so no subscript there. So, okay, so then, well, I still know that it's just 1/2 mv squared, and we said in this case, at the beginning here, it was 1/2 m of the mass 4 and 5 times whatever velocity it had squared. Okay, because we had two of those spheres going in. So then how much we must have the same amount of kinetic energy at the end. The kinetic energy at the end must be equal to this kinetic energy before that collision. We can't create or destroy energy. Okay, great. So then I know that it's 1/2 m of 4 and 5 together times its velocity squared. But that's going to be equal to like some kinetic energy, 1/2 mv squared of something else. Well, what could that something else be? Let's ask a question. Could it be that just one of those masses kicks out there? So it would be just the mass of mass 1. And we're assuming that all of these spheres here are the same mass here. So could it be just of mass 1 there times its velocity squared? And we'll put the velocity of the ingoing bit there as v naught there. Could it be that? Well, we know that this is half of that mass. So this guy right here is 1/2 if this guy is 1, right? So this is going to be double of whatever that is. How you could make up numbers if you want. So then, wait, if it's got the same velocity there, if it's got half of the mass, and each of these things has to equal each other, then it's going to have a greater velocity there. Okay, so maybe one outcome here, and this math of what we've done in energy here supports this, is that one possible outcome is that one of these spheres kicks out, but at a higher velocity. Okay, all right, that's one possibility. Now, you might have said, hey, maybe not just one comes out, maybe two of them come out. So let's draw that as a separate case here. So we don't know exactly how many come out, so I'm going to draw something in here. Well, maybe I should finish this drawing. If only one comes out here, so then this is number 1, 2, 3, 4, 5, and maybe I'll put it in the strings here. All right, but what if two of them comes out instead? Maybe that would happen. We're not sure. Would everything, that energy that we've studied before, support that that's possible? Well, let's do the same type of energy thing here. Here, we know that the ending kinetic energy is still 1/2 mv squared, and it's got to be equal to the original bit there, and the original bit was just 1/2 m of 4 and 5 added together times whatever original velocity that had, and that's going to be equal to, well, we're going to say that number 1 and 2 come out now. And so that's going to be 1/2 m of 1 and 2 times its velocity squared. Now, the mass of 1 and 2 and the mass of 4 and 5 are the same as one another, since the mass of each of these spheres is going to be equal to one another. So then these masses are the same. So the masses in this case would actually cancel out, because I could divide by those, so the same quantity there. The 1/2s clearly cancel out because it's just 1/2 on either side. And so now I have v squared is equal to the original velocity squared. So that means that if two of them came out, these two that come out would come out at the exact same velocity as the two that were coming into it. That would work as well. Now, we could keep going on with this, and could we have 3 come out? Yeah, we could. This will support that 3 could come out, but similar to what if just 1 comes out, when we had 1 come out, the mass was less of coming out than the mass coming in, so this velocity had to be much greater. Maybe I should like write that out there, that this v squared is going to have to be greater than the original velocity squared, right? And that's what, you know, having these different masses here say. Well, a similar thing is going to be true if 3 of them come out. If 3 of them come out, now we're going to have triple the mass, or not, well, we'd have 3 masses over here and only 2 masses over there. And so now this velocity would have to be smaller. Yeah, so the energy says that we could have 3 masses come out, and it would just be moving a little bit slower. Now, here's where this online thing is a little bit less effective. Let's go try this. We've now looked at everything that we've figured out thus far about energy and applying it to this new scenario here. And we've come up and seen that we have at least 3 possibilities. 1 coming out when we have 2 come in, 1 comes out at a faster speed. Or we let 2 come in and 2 come out, but at the exact same speed. Or we could have 2 go in and 3 of them come out, but at a slower speed. Maybe we could have 4 come out, but even slower. Maybe we could have all 5 go, but then again, even slower. Okay, so all of these things are going to be valid when we go through and do our energy calculations. And if I made up numbers here, it all works out fine. Well, let's go to the actual world, the real world, and see what actually happens. That would be interesting here. So if we go and we play this not at normal speed here, so we can go at a reasonable pace here. When I have 1 come out, only 1 goes back in, and I think he then pulls out 2 in the next example here. My internet's not so fast here. If I can get to the right point. I could just skip to the simulation here. And he's probably explaining a bunch of stuff. I have my sound off, so I don't even know what he's saying. And we're just going to go to the simulation. So he probably does that at some point. Let's go to a simulation since I don't have the physical example to be able to show you. Now, I found a couple different simulations here. This first one that I'll show you is from... actually, I don't want to show you this first one because I can't show you this. The first one that I'm going to show you is this guy right here. Let me move this over. Okay. So I found 3 different simulations here that all model it in some good ways. And they all do a good job in some ways and a bad job in another way. So let's look at this first one. It looks kind of kitty here. They kind of give you this nice perspective, but it looks the same as the video that I just showed you. If we try this out, it sure does match that physical example that we've seen the video of. 1 comes in and 1 goes out. And if you look at it, it kind of looks like it's coming out at the same speed. Great. If I have 2 come in and let this thing go, 2 go in, and 2 come out. And if I, try it a bunch of times here, and if this was a physical, if I actually had the thing, I would try it for you. And every time that I do this thing in the real world, every time I do, not just in the simulation, but every time I do this in the real world, when 2 come in, 2 come out. And notice that middle one just stays exactly where it is. That happens every time. Now that should be a little bit odd for you, because if that happens every time, why is it that when I looked at energy, it said that multiple things might happen? Because what are we trying to do in science? What is science actually trying to do? Well, we're trying to organize all of the knowledge of our world. But ultimately, what are we trying to do with that knowledge? We're trying to do something useful. And making predictions about the future is probably one of the most useful things that we can do. Why is that useful? Well, I can build things that go on and do something else. And I don't have to do trial and error every time to build that thing. I can figure out ahead of time what will work and what won't work. And clearly there's a bunch of variables along the way, so I might have to build prototypes and such. But I can get there without just pure trial and error. And that's how we've gotten to all the technology that we use on a daily basis, how we have cars and all these advanced machines, as well as computers and phones and such. It all comes from us understanding how things work, applying that, and then making some prototypes and actually getting it to work in the end there. So making predictions is probably one of the most useful things that we as human beings do. And if I have some knowledge, like with energy here, that's only partially complete, that says, hey, multiple things might happen, but only actually one thing happens, well, that's not so useful. By itself, that's not so useful, because now, how am I going to go and build something with that? Because I don't actually know what will happen without actually going and doing it. And then, going and building things, it takes a long time. So there's something else going on here. There's some other bits of information that we need to be able to actually predict what would happen when I bring out 2 and have it come in. And we can go and annotate this here. This thing doesn't happen. This thing does happen. And we talked about the 3 coming out and the 4 coming out, and we talked about the 5 coming out. None of those happen. Only the one happens. When I drop 2 of them in, 2 of them come out. What is this other thing that is not just being conserved, or that what is the other thing besides energy that's being conserved here? And the other thing, you guessed it, is momentum. That if I take the idea that we're going to figure out in just a few minutes here of momentum, and I apply momentum to this situation, momentum and energy combined, since both of them will be true, then when I apply that, only one option will actually work. In theory, when I actually work it out on paper, only one prediction. I would only make one prediction of what would happen in the natural world, and it would be this case right here. And then when we go and test it, yep, that's exactly what happens. So energy is part of the picture, but it's not the whole picture. And some cases, when I go and look at the world, I can use just energy, and I can successfully figure out how things work and what will happen by just looking at energy. But there's other cases, like this case right here, where if I only use energy, I only know part of the picture, and I only can explain or predict what some things might happen, but won't actually know what will happen. But if I have a more complete picture, like both energy and momentum combined, I then can combine these things to actually get to what will actually happen, and then confirm that, or refute it for that matter, with an experiment. And so momentum does this. Okay, cool. Sweet. So that's why we're doing momentum, and momentum is incredibly useful. And let's get into what momentum actually is. Okay, so I'm going to actually pause the video. I'm going to stop the video, and I'm going to make a separate one, because that was like the intro, and now we're going to make the real thing.